Hey folks, today I want to go through a system design for a ticket booking app like Book My Show in India or Ticketmaster in the US. So let's get started with that. System design ticket booking app, Book My Show, Ticketmaster. So in order to get started with the design, first of all we need the functional and the non-functional requirements for the system. So let's start with functional requirements. The first requirement is that the user should be able to book a ticket. So that's the first requirement. User should be able to book a ticket. Then in order to book a ticket, the user should be able to view an event. So user should be able to view an event. And then in order to view an event, the user should be able to search for different events as well. So user should be able to search for events. So in any such kind of system, there are two sides of the requirements. One is the user side, the user who wants to book the tickets and search the events, and then there's the other side where the admins can add certain events or onboard certain venues and so on and so forth. That part, the admin part, is something which we are keeping out of scope for this particular design. So let me write that out. Admin side of the platform. Let me update this booking platform. So this platform. So this would be add events or venues, etc. Then we are also not adding the functionality for a user to look at their past events. What were the past bookings? User should not. Past events user. Then there is another functional requirement where something kind of personalization. We have some, let's say, kind of ML model which gives very specific personalized recommendations to the user. That is also out of scope for this particular system. So recommendation system to the user. So these are the functional requirements. Now let me go to non-functional requirements. And the first requirement is low latency. User should be able to search and view events almost real time, let's say 500 milliseconds. Second would be so now talking about CAP theorem. CAP theorem talks about that consistency and high availability cannot there has to be some compromise between these two factors, these two facets of the system. But the cool thing here is that we need consistency in one aspect of the platform and high availability in different part of the platform. So we need consistency with respect to ticket booking, that is there should be no duplicate bookings of a ticket, and for high availability we are talking about viewing an event, searching an event. So consistency for ticket booking, which is no double booking, and high availability for this is your search and view events. Okay. Then we should be able to handle surges. So let's say a scenario where, let's say, Book My Show is responsible for ticket booking of the World Cup final that's happening in India. So I would want my system to be able to handle such surge when the ticket is made available. The user should be able to, the system should not break down because X number of users have immediately come to the platform. So search cases where high volume of users suddenly get to the platform. And the fourth part here would be that my reads would be greater than writes, in the sense that I as a user would search the events very often, but my conversion rate of booking that particular event into a ticket is very small. Let's say around 1%. So my reads will be much more than my writes. Now let's talk about some non-functional out of scope requirements as well. And these would be, let's say we are not going to work upon a CI/CD pipeline, or we are not going to work upon a monitoring and logging system. Now there are other type of requirements which are not, at least in the common user conversation, which are not so much important, but they are important nonetheless, and there's very strict guidelines, at least in the broad. EU has the most important guideline of GDPR, which talks about privacy. So that also is out of scope for this particular design, though it is very important. These are the functional requirements and non-functional requirements, including out of scope for each of them. Now let's talk about the core entities, which would comprise our system. So let's go to core entities. And the first core entity would be a ticket, that the user should be able to book the ticket. That is the most important entity. Then we have venue, then we'll have event, which event are we booking the ticket for. Then we'll have a venue, where that particular, in which geographical place that event is being organized. Then we will have another entity, which is bookings, and there are different ways to go about it. You can or cannot, or you can decide not to have booking, but I see that there is some loss of information if we let go with the booking and use only ticket as the primary source. So we will have a booking entity as well. Then there'll be user, there'll be artist, which are going to perform that particular event. Let's start with them, and we'll add more if required. Similarly, let's talk about the APIs. And you need to remember that we are not talking about the admin side, so there would be no post API for event or tickets or venues or whatever. So the first API would be, let's start in the opposite direction here. So user should be able to search for events. So this will be a GET request, and there would be a search endpoint. And then when I'm searching an event, I would be able to, let's say, have an artist, or search by an event type, or search by date type, or I can just have a wild random search, which is just term. So this API will look like term search term equals to term and percent date equals to date, and this would be lower bound upper bound, ampersand type equals to something, and ampersand, so this will be event type, ampersand artist equals to, and so this could be a very complicated long query, and this would give me a list of events, and there would be certain details, but it will not have the ticket details. This will just be a list of all the events and the dates and the artists and so on and so forth. Then the next API is a GET API again for a specific event. So we have event / event ID, and this will give me an event object, which will have the ticket objects as well, which tickets are available, which are not available. It will have the performers, the date, some images pointing to that particular, some URLs pointing to the images for that event as well. And the third and the most important, most critical as well, sorry, excuse me. The third and the most important and most critical part of the API here would be when the user want to book a ticket. So this will be a two-step process. There would be one part, the first step, where the user will reserve a ticket, and the second part will the user complete the payment, and then a ticket will be booked for the user. So this will be a two-part API. The first will be post, and it will be booking. Here we will take certain IDs. So we'll have a ticket ID, and this could be a list as well. Let's say the user want to book multiple tickets at a point in time, and then there would be event ID. Which event? The important thing to note here is that I am not going into detail about what the core entities will look like, what would the data structure look like, ER diagram look like for these. We'll come to that once we are around the database part of this particular design. The other important thing here is that there is no user information in these APIs. For example, there is no user ID. And the reason is that if we add a user ID in the payload, this might lead to a security concern in the API, in the sense that if a hacker, if if someone with a malicious intent gets to know about the user ID of a particular user or a few users, then they can very easily impersonate that user and make a malified booking. So the good way to go about such cases is use the user information is stored in session tokens or JW tokens, which is in headers, and the API is responsible for retrieving these values from the header itself, and then use that information to book the ticket, to identify the user, and then book the tickets on his or her behalf. So yeah, these are the APIs, and once this is done, I would now move on to the system design part of this particular system, which is the high level design, and let's get started on that part. So yeah, now this is now the high level design. So first of all, we will have a client, which could be a web client or a mobile client. So client, and this is the user. The first API is that they should be able to search the particular event, so different events. So this will hit a API AWS API gateway, and AWS API gateway does a couple of things for us. It does the routing, it does load balancing, it also does authentication, among other stuff. So this is self-managed. This is the go-to system for go-to solution for these kind of systems. Yeah, okay. So what the user will do, the user will hit a API request, which should be get /search, and to cater to this request, we will have another service. We'll have a service which is, let's say, search request, search service. So search service will hit the database, get events, and then it will have the terms. So search service will hit let's say a primary database, and this database is capturing all the information related to our events, our performers, and so on and so forth. And maybe this is a good time to talk about the entities and their relationships in the database. So the first entity I would start with is a venue, though it might sound like, this is not so important and we should be talking about the event first, but I'll start with venue, which will have ID, which will have which will have city, location, etc. And there will be other metadata associated with it. There would be another mapping which would be, let's say, a kind of a list, and it would be tickets. This would be something like a seating arrangement. Then we will have a ticket table. Sorry. Then we have a ticket table which again has an ID, which will have a VID or venue ID, which is primary key. Then this will, I'm not adding dates here, we'll come to dates in a while in the booking section or in the event section. So we have booking, we have ID ticket, we'll have let's say the class of ticket. This could be silver, bronze, gold, platinum, etc. We'll have the price, and this price, let's keep the price here for a while, though there would be different prices for different venues, and the way I'm structuring it would would not be possible for that kind of situation. But sorry, I said there will be different prices for different kind of events. For example, if I have a very low-key event where not so famous stand-up comedian is performing at let's say a restaurant, a cafe in New Delhi, the rate would be different. But if, let's say, I have Abhishek Upmanyu coming in to host, the price will be different. So we will need a different way of handling these situations, and that could be achieved by having a different price table in which will point to these tickets. But let's keep that as a side. We'll for now keep that as an out of scope thing. So yeah, this will be and then there will be other metadata which we can add later if required. Then we will have the event object, which again will have an ID, and this will have a venue ID. This will have a date. This will have artist. So the date would be this, and venue ID would be a primary key. Then we will have date. Then we have artist. This again is primary key, and description, obviously name. Then there would be the metadata. Then we will have another table by the name bookings, and this will have an ID. This will have ticket ID. This will have event ID. These two are foreign keys. Sorry, this is not primary key, this is foreign key. Similarly, this also. So we have a ticket ID, which is a foreign key, and this also has a foreign key. And then we'll have a user. To which user does this booking belong to? This is also a foreign key. And then we'll have a status, which is available or reserved or let's say booked. And then there would be other metadata which I might add to later. And then we'll have some other not so important, not so relevant for this discussion entities as well, which I will not go into detail. So let's say we have a artist table, we have an ID here, and then we have metadata. And yes, so now this is a search service. The search service will be queried upon will query the primary database, and by the looks of it, these are a lot of interconnected entities. So we'll go with a SQL database. Let's say use Postgres for this, which is one of the most common database solutions out there. And for now, let's just assume that this would be a very rudimentary query, which will be let's start from, and then there would be a very complicated complicated terms here. This will be very slow, but this will not be optimal, but it will get the work done at least. And for now, let's just stay with it. I want to go through the complete design first, and then we'll come to the nuances in this particular design. So here we have the search query, search service. The user gets the result where he or she has the event IDs. There's a list of events which are happening in their area, and then the user decides, okay, I want to book a ticket for a stand-up event that is happening near my locality on so and so date. So then the user will and the user wants to look into the details of that particular event. So then we'll have again a get event API, and this would be EID, so which would lead to event CRUD service. So the other parts of creation, updation, deletion are out of scope for this particular design, but we are going to read the event as well, event through this service. So event CRUD service. The system API gateway makes a call to this particular service with the event ID, and what this does is, again, it talks to the same database. It gets the relevant information about that event, queries all the relevant tables, and then creates a event object out of that particular your query, and gives it back to the user. The important thing to note here is that in this particular case, in this particular flow, the service will request, will make a query on bookings table as well, and figure out which of the tickets, which of the seats are booked as well as reserved, so that if the user wants to book a ticket immediately, the user should have correct information of which tickets are available for me to book. So yeah, and then we have the last service, which is my where I allow the user to book a ticket. So this will be a booking service. So now the user has decided to book a ticket. Okay, I'll just keep it here. And now the user is making an API call here, which is post/booking. It will have details like ticket ID, venue ID, which are added here. Okay, so sorry, I forgot to add an API point here. So the fourth API point would be patch. It will be on the booking, and the parameter which we will be passing here is booking ID, which will be mapped to the ticket ID and the event ID internally. And then there might be some payment details which are provided by the service, the API gateway in the previous request, or this might just lead a user to the confirm booking place, where a series of webhooks and integration with a payment gateway allows the user to book a ticket by making the payment. We'll come to that in a while, but yeah, this is the fourth API which I did not add earlier. Now the user has made a post booking request here, and this particular flow will go here. So create booking with TID and EID. Now this is a booking service, and what it will do is, it will again talk to the same database. It will create an entry in the booking table for this particular ticket ID on this event ID, and then we'll mark that particular ticket as reserved. We will we'll move the user to another screen which will have a payment gateway integrated. The user is supposed to make the payment gateway. So payment gateway is like, let's say, Razorpay, or I think Paytm also has a payment gateway. If not, that's fine. There are other payment gateways like, let's say, Stripe or PayPal. So what the next booking, the user then makes another API call, which is patch booking with the booking ID. So this could be complete booking or something like that, and then this would be again booking ID. Okay, so we lead a user to a payment gateway where the user performs the payment, and then a webhook is registered to that payment gateway, which calls back our service upon successful payment. Upon successful payment, we update the details in this particular booking ID, and this reminds me that there would be another field here, which is, let's say, payment ID, and in this particular flow we will update the ticket to booked. So now it is completely unavailable to be booked. Now so this is the flow, and this is a very small functional flow that gets the work done, but there's a problem here, and the problem is that okay, this is interesting. Okay, the problem here is that, let's say a user has made a patch request to that particular booking, and in the patch booking status we reserve the ticket for the user, but and there's a window time limit of completing that payment in, let's say, 5 minutes or 7 minutes or 10 minutes, but in that duration the user does not complete the payment. The problem now here is that this particular ticket is now booked for entirety, because while getting the tickets, we make sure that only the available tickets are fetched back to the user. So now the user sister or brother or any other user comes back and wants to book the same ticket which was earlier reserved by user A. That ticket is in reserved state, and we will not be able to give back that particular ticket to the user. So that is not a great user experience. What we want is, after 10 minutes of creating that entry of reserving that ticket, the ticket should become available by itself. So there are multiple ways to do it. One, what we can do is we can have a timestamp here, which should be, let's say, booking timestamp or rather reservation timestamp. And whenever this query is made, we check the timestamp of that ticket as well, and then we do a diff of that timestamp with the current time. And if the time difference is more than 10 minutes, we make the ticket available. But again, this is very cumbersome. We'll have to do it for every ticket, and this is not a great idea. Another solution following the same line of thought is that we have a cron job here, which, let's say, runs after every 10 minutes. And this cron job queries all the tickets, all the bookings in this particular table. It does the same work, which is checking the timestamp of that particular reservation. It checks the current time, and if any ticket exceeds that time window, that time difference, it marks that particular ticket as again available. Again, the problem here is that let's say a user started booking a ticket at or the window expired at 12 p.m. and the cron job ran at 11:59 p.m. 11:59 a.m. So the next cron job will run at 12:09 p.m. So the ticket is booked for 9 minutes extra when it should have been available. So that's a problem here. And the way to get around this is we will get rid of this cron job. We'll get rid of this thing. We'll have another lock here, which is a ticket lock. Now what's the ticket lock? This is basically distributed lock, let's say Redis cache. So it's a distributed cache, which is Redis, and this will keep track of the tickets which are booked or which are reserved. Now how it will do it? This has something known as TTL, time to live, and we can, whenever a user wants to book a ticket, we make an entry in this particular in this cache, which is, let's say, ticket ID, rather booking ID. What will this look like? Yeah, booking ID, this, and then we'll have a TTL of let's say 600 seconds. Now what this does is, now whenever we have, so the user comes here, the user makes a request. First of all, here the service makes a request, adds a key value pair here, then it makes a request here, and the tickets are written back. Now the user decides not to book that ticket. So after 600 seconds, this particular entry will expire because that particular ticket was not booked, and this will lead to that particular ticket becoming available again. Now when I am making a query to figure out which tickets are available, I'll do two things. I will first of all make a query here which will give me the list of all the available tickets which are returned from here, and then it will also do a query here which will check which tickets are in reserved status. So just to sum it up again, what this particular request will do, it will first of all check what are the tickets for that venue for which the event ID has been given. So I have an event ID here. I will map that event ID to the venue ID. From venue ID, I can go to tickets, and I will have all the tickets which are available on this particular venue. Then I will do two more queries. One, I will go to the booking table and check for with this particular venue on this particular event which tickets are in available state, and out of all those available state, I'll also check which tickets are logged here. So I'll just remove those tickets as well. I'll filter them out, and then I'll give them back to the user. Now user comes here, he or she wants to book the ticket. They have made a booking, and when they are making a booking, I make an entry in this Redis lock, in this ticket lock, which gives an entry, which makes an entry for this particular booking ID. After that, if the user does not book the ticket for 600 seconds, this entry becomes kaput, and then this is again free. And if the user makes a booking, then after that we make an update entry here which makes the ticket as booked. So this way we can make sure that that user experience is we are able to show the tickets which are reserved but not booked, reserved for more than 600 seconds but not booked. That is one thing. The other thing which I wanted to point out here is that there's something in my mind I want to talk about, but okay. So yeah, that's it. So that sums up our high level design, but as you mentioned, there are some areas to streamline, to iron out here, and then that's what we'll be talking about now today. So the next thing is, if we go into our non-functional requirements, the first thing is this low latency, that the user should be able to search and view events almost real time. But if you look at this part, this is very slow because we are doing a request on SQL database and there are multiple indexes. The scan would be huge, and this will not be the most optimal solution, the most optimal query. So what we can do now here is that we can have Elastic, not Elastic, search optimized DB, which is something like, let's say, AWS Elasticsearch. So we have a search optimized DB, and this is, let's say, Elasticsearch. And instead of hitting the primary database, our search service will hit this particular database. And for now, let's assume that our search optimized database has all the relevant information for all the events. The way search database works is that search optimized database works is that it creates an inverted index for all the events. So for example, I have an event which is, let's say, Cricket World Cup final, and I have the different teams, I have the different venue, and so on and so forth. I have a date and all those things, and I have a list of such events, such entries in my database. Now the search index database will create an inverted index of that particular entries. So let's say if I will just input cricket it will have a JSON a mapping system where so there are different rows in that index in that database. So row 1, row 2, which are called as documents, and these are all the different events in there. And out of this JSON data, it creates an inverted index, which is kind of let's say index at the back of the book. So at the back of the book you have, let's say, a specific term, and then there's a reference to all the pages where that term is present in the book. So you can just go to a term and then look back at all the page numbers which are a part of that, which have a mention of that particular word. So the reverse index works the same way. And if I have an entry by the name let's say cricket, then that will be ranked higher. So I will make a request to this particular search optimized DB, and it will give me back the result. Now the question is, how do I make sure that these two systems are in place? One solution is that instead of using primary database, you just make this the primary database. But it has been observed that search optimized DBs are not a good source of primary databases. So what we can do is we can have a complicated system in our event create service, which makes sure that whenever we are updating, creating an entry in the primary database, we also make an entry in the AWS Elasticsearch. And this is from the user, from the admin end, so we have not gone into that detail, but this part is relevant. So what we do here is that now we have two different flows. Whenever we are writing a new event or a new venue or whatever, we are making entries to both these databases, and that leads to a lot of very complicated logic which we have to write here. That let's say the write fails, then we do not need to proceed here, or if the write fails here, then we roll it back here, and it's not the optimal, most ideal solution. What we can do instead is have a CDC, which is change data capture, and the kind of CDC we will use here is Kafka. So what will this do is that, let me just move all these entities a bit to the right. Let me move this up, and yeah. Now, whenever I make a change to the primary database, there will be some consumer listening here in Kafka, and then there will be some producer here, that data would be produced, and then at the end of Kafka there would be some consumer which would write the data to our search optimized database. So this way we can ensure that our search database is almost always in sync with the primary database, which is our Postgres here. So that's how we can make sure that the queries are fast. Now this particular part, the search queries, so Elasticsearch will be able to provide our very complicated queries, which I have added here in a faster way. Yeah, and one of the ways now is to, how do I make sure that this particular result is wicked fast. Let's say there are different users who are querying this particular search terms very often in the lifetime, in a very small time. So there are different ways we can do that. One is that we can have a cache here, which is again a Redis cache, and that caches the queries, and just gives them back very fast to the user. The other solution which might be useful here is that we have CDN system. We will have a CDN system which will take care of our the images and relevant stuff. So we can cache that result at the CDN as well, which is nearer to the user. So in that case, the results will be much faster. The caveat here is that in this particular system design, we are thinking about no recommendation to the user, so that will work. But as we start giving more and more specialized recommendation to the user, that CDN, that caching will fail in that regard, because we might have a term which is, let's say, the location of the user, and the location could be very precise to the level of the lat and launch of the user. So then every query will be different, and it could not be mapped to the other queries which other users are doing in the vicinity of this particular user. So we can have a Redis for caching, or we can have CDN. Any of the solutions will work. And let me just move all of this a bit here so that I can move this thing here. So yeah, I can have a CDN here as well. Rather, let me put this guy here. So that way we can make our queries much faster and take care of this particular part, this non-functional requirement, which is on low latency. Now, there's one thing which I was about to talk about earlier, but I forgot. So why do we have this ticket lock as a different entity and not as in memory in this service? And the reason is that this particular CRUD service would be scaled horizontally. So we will not be able to save that state and give back the and make sure that what ticket has been reserved by machine A is also visible to machine B or machine C. So that's why we have a distributed lock, which makes sure that all the machines, depending upon how the system has scaled, are able to access which particular tickets have been booked and which are in reserved state, and then give the correct information to the user. So going back to the non-functional requirements, the first part is done, which is this low latency. Second is this consistency for ticket booking, no double booking. This is something which we have done already. The next part is this search cases. Now, let's say the World Cup final tickets are opened. The World Cup is between India and I think Australia, and a lot of users immediately want to book the ticket. Now, how do we make sure that the system doesn't become overwhelmed? It does not scale as fast, and also we want the user of different places to be able to book the tickets. We do not want a situation where, or rather we might not want a situation where the moment the tickets are opened, all of them gets booked. So one way we can do this is we can either release the tickets in batches. So we will communicate to the user well in advance that the tickets will be made available on XXXX dates, XYZ ABC dates, and then we release only a specific quota of the users. But still, in this situation, the number of users who want to book the tickets will be huge as compared to the supply. So there's a huge supply mismatch, and a way to handle that is either we scale the system horizontally well in advance, or we have a queue in place, which is, let's say, something like a virtual waiting queue, and it takes care of all the users which are hitting the system by putting them in the queue, and then we periodically move those users one by one into the booking service. So let's say we are going to release 100 tickets at a time or 1000 tickets at a time. Once the 1000 tickets are booked, then we let the users, the next set of users, go and book the tickets. So this will require some kind of conversation with our product team, but there is a way how we can manage this. So we will have, let's say, let me add that particular queue somewhere here, which means this guy should come here, and I have and this again could be Kafka. Kafka is a good solution for this. So that is one part, and there's one more thing here which I forgot to talk about earlier, was this consistency. So we have managed consistency here, but there's a problem. So let's say I as a user open the event window and it shows me that out of 100 tickets 50 are available, 50 are booked. But the moment I have made that request, that get request for that event ID, that information stayed. It is possible that after I open that particular window, the users all in the globe might be booking that particular ticket, might be booking tickets for that particular event. So let's say if I want to update tickets, book a ticket after, let's say 5 minutes of me opening that window, I might end up realizing that out of those 50 available tickets which were available earlier, only 10 are available now, 40 are booked. And this is not a great user experience, though a lot of platforms get away with it, but there are ways to handle this. So what we can do is we can have a persistent connection between the client and the server, and this would be a two-way communication where the server can also send some information back to the client without the client requesting for that information. There are two different ways of going around this kind of a system. One is the WebSockets, which is a very widely used solution, and it will work here. The other solution could be a server-side event, which I have not implemented, but I have come to my knowledge that it works similarly, though the functionality is very different. So what will happen here is that whenever a ticket is booked by someone else, a server-side event will trigger, and then the server-side event will let the user know that this particular seat on this particular event has been booked and is not available anymore for booking. So that way we can give the user a very real-time information about which tickets are available and which are not. So that will lead to a good user experience. Now coming back to search cases, we have talked about search events, we have talked about consistency, we have talked about low latency. The last thing is reads are much greater than writes, and for this we can either have a replica system or caching, or we can use a NoSQL database which supports a lot of high read system. But as we decided earlier that the Postgres, we are using a SQL database, so a better solution could be some kind of master slave architecture which takes care of high reads. So that's all for today. I think the system works well. I might need to work a bit more on this part. I don't think I was able to explain that completely. So I'll go back to my notes and figure out how do we take care of such situations. Now, just like the last time, I wanted to talk about which sources I have used for preparing this particular system design. There are two videos, two resources. One is your designing Ticketmaster, again by System Design, Hello Interview. And then the other, so this is exactly a ticket booking platform. He has used something known as Ticketmaster. He has replicated that part. And the other thing which I used was something by Scalar around booking hotel booking website. And what I have done here is that I have taken the best of two worlds. For example, in Hello Interview this video, they do not talk about this particular booking table. There is only ticket table. While in the hotel booking this thing, we have I think inventory table, which is kind of a counterpart to the booking table. So these are the two resources which I've used to prepare this interview and this system design. And I think that's it. So that's it for today, and hopefully I'll come with another system design in the days to come. That's it. Bye. Thank you.